Hi, this video will introduce you to the workflow to set up a galvanic corrosion simulation under bulk condition, as well as setting up the configuration to use STAR-CCM Plus along with Cordesa's corrosion gene database. Let me show you first how to set up STAR-CCM Plus to read Cordesa's corrosion gene database. You should have received from our team a couple of different files. You should have received the MDB file, which basically contains a corrosion gene database. And you should also have received these three files that are for the license itself. Okay, let me tell you or show you where all these files are. I personally like to put these files, the license required file, on my user folder. It can be anywhere else. It can be in your documents, download, C, whatever. But just remember the exact location you saved this file because you will need to read them from STAR-CCM Plus. In my case, you will see that in a minute. I copied these three files in my user folder. So users, J Mendes, this is my user in my computer, and I created a folder called Cordesa. Here we have this file and these two directories. The other file that you also have to copy over to your computer is the Cordesa MDB file. Here's where basically again we have corrosion gene database. So you copy and you have to paste this exactly in the data file from STAR-CCM Plus. So in my specific case, so we have program file, that's where we install our program Siemens. This is the folder created by STAR-CCM Plus. Once you install that, the version of STAR-CCM Plus folder, star, which is another directory, and then data. Here in data, that's where you have to paste the MDB file. So we come here in Continua, select models, and we select liquid. Of course, it will be three-dimensional. Segregated flow, constant density, steady, inviscid. And here we come here where it says electromagnetism. We click on electromagnetism, electrodynamic potential model, and then we're going to see a new model here called corrosion. We click corrosion, and after that we just close. After that we have to update the electrical conductivity for the liquid. In this case we're using 3.5 sodium chloride, 3.5% sodium chloride, and we have to use or set the right electrical conductivity. In this case is 5 Siemens meter. Okay. Here is where we have, after we set this up, now we can select the materials. So we expand, we have the surface material node that we have to expand. Then we come here where it says surface material and we do right click, select surface material. And here you're going to have Cordesa and standard. If you didn't update the MDB file, you are not going to see this file over here. Okay, so since we already update the MDB file on the directory I showed, now we have access to this database. One important point here is that you can have your own material database. So in this case, this is a commercial database we have, but of course we have other materials, other databases for some other customer, like for example, like Air Force, they have their own material database, which is private to them. Yeah, for this demo, I'm going to pick two materials. I'm going to use 7075, 7075 T6, okay? And I'm going to use bronze for the bushing itself. Copper alloy, bronze, this one over here. Nickel bronze, this one over here. Okay. After I select these two materials, I click apply and then close. Don't be worried about this warning. This warning, what it says is, look, you're using a corrosion library, but there's no license attached to it yet. So don't worry about that. The good thing is that we see here our material that we have already imported. Now we are ready to assign the boundary conditions. Like I said, this is the mesh. This has a block outside, and I did a subtract operation. Now I have here my bushing, and I also have my plate. So the substrate here, I'm going to assign here, we come down here, electric potential specification, and we assign surface material polarization. And after we click that or we select that option, we see a new tab or a new node here called physics value. And here we come here down to surface material and we select aluminum 775. We repeat the same procedure for the bushing. So we come here in the bushing, we expand this node, electric potential specification, and we assign surface material polarization. And after that, we see a new tab here, a new node that opens up. And here we select the other one, copper alloy nickel aluminum bronze. This one, the outside block, is an insulator, and the STAR-CCM Plus assigns all walls as insulator, so we don't have to do anything here. Okay, now let's import the library. Or in other words, let's just call or read the license. So we come here in Corrosion. Here's where it says library. You click this button over here, and you basically go to that directory where you have your library. Like I said, again, I go to users, J. Mendez, Cordesa, right here, and Windows, and you read this file over here. And that's it. Something I would like to repeat here is that check that we actually selected the .dll file in the Windows directory, but the actual directory contains multiple files in that Windows directory, and the one that we loaded on STAR-CCM Plus or read in STAR-CCM Plus was this. So please do not change the information that is inside of these different directories. As well, this license has to actually be outside these two folders. Just keep that in mind. So in this case, we create a scalar scene. I will call this corrosion rate. And I like to create as many displayers as materials we have. In this case, we have two materials, which means that I will turn this off. Which means that I will need to create another scalar for the second material. So let me go here, new displayer, scalar. And in this display, I'm going to select only one of the materials. In this case, is the material 2. And here we select in the field function corrosion rate. Corrosion rate. To make things easier, change the units to microns per year. That's the typical unit we use for galvanic corrosion or corrosion in general, but you can feel free to use any other option. In part 2, we're going to select the other material, material 1. Let me just make sure that I selected the right material. So here we have bushing, okay, and here we have material 1. That's fine. Here again we select corrosion rate, and we change the unit to microns per year. So at this stage we are ready to run the simulation. It's just good practice to create a report to make sure that the charge or current is conserved. So in this case we usually use the surface integral. Let me look for the surface integral of the boundary specific surface integral right here. And here we use the boundary specific electric current. Boundary specific electric current. This is similar to, for example, a mass imbalance. I mean, you want to you have to demonstrate that your solution is accurate from a numerical standpoint, and we usually check mass imbalances. So in this case, we just check the current imbalance. And here we select all the surfaces, including the block surface here, which is an insulator, just for to be consistent. And here we just check this boundary specific electric current, and I like to create a monitor and plot from this report. So now we are ready to run the simulation. We just click run. And I'm going to pause the video here because this could take some minutes. Okay, after the simulation completed, here I want to showcase the importance of creating that specific report that we created, the surface integral boundary of the boundary specific electric current. And what you can see here is that the residual for the electrical potential is indeed really low, -13, E -13, which is pretty much machine precision. Nonetheless, the imbalance of current is absolutely high. And even though we could consider this converged based on the residual itself, it is not converged because the imbalance is absolutely high for this case. So we had to add a little bit of an under relaxation, and we see that the solver struggled in this section over here, but after adding a little bit of a under relaxation, we were able to get to the right solution. And notice how tight this boundary specific electric current balance is. So now at this point, we are confident that the solution has not only reached a numerical threshold in terms of the residual that we usually do, but also an important metric, which is the surface integral boundary specific of the boundary specific electric current. Okay, after that, this is the scene plot that we set up. In this case, what we see is the plate is actually the anode in this case, and by plate I mean the substrate. In this case is the material 01, because that's the one that is showing a corrosion rate of 14 microns per year, while the corrosion rate on the bushing is 0. So in this case, the bushing is the cathode, and whereas the anode in this case is the plate, which is aluminum in this case, if I'm not mistaken. So just to confirm, yes, it's 775. So aluminum is corroding at a rate of 14 microns per year. Again, this video, it's the only purpose of the video is to showcase the workflow to set up galvanic corrosion workflows in STAR-CCM+. Thank you very much.